In the first video I described what I think nothing is, or more appropriately what nothing isn't. Now I'd like to try to describe what everything is. And it's really not everything. We don't have to explain how to program a computer. We don't have to explain how to design an aeroplane. But we do have to describe the fundamental principles upon which everything else depends, so that we don't have to, or so that we can explain more complicated things that have happened or which can happen now based on what happened in the beginning. And so I'm going to describe what is necessary, what information is necessary to be able to say confidently that we have a theory of everything. The most important thing is to describe the variables that were created when the universe was created, because most of the variables that we talk about, such as velocity, force, energy, momentum, and so on, most of those variables are discoveries or decisions that man has made in order to explain more easily more complicated things. They are summaries of information rather than raw information. You only need very few, and I think only about 4 very fundamental variables. Now, traditionally we have considered mass, length in space, and time as the most fundamental variables. But since Einstein pointed out that time is not absolute, well, mass is not absolute, time is not absolute too, but mass is not absolute. It is a relative variable, because the mass of a body is its resistance to being accelerated, and this depends on its velocity. And the more rapidly things travel, this is since the speed of light was measured and determined to be constant, that if nothing can travel faster than the speed of light, then you can, as you get faster, then obviously you're going to be affected by that, and that's another subject. We're not going to go into it now. But mass is something that is not an intrinsic property of a body, and so I've decided as far as I'm concerned, to divide mass into 2 parts. One part is energy, which Einstein pointed out is pretty much the same thing as mass, but it is a little different, as I'll explain. And matter. Now, matter is the amount of substance in a body, and this is something that doesn't change. When a body gets more massive as you accelerate it, particles in the Large Hadron Collider, for example, in Switzerland, when protons are accelerated to close to the speed of light, they become much more difficult to accelerate and cannot be made to travel faster than the speed of light. What we have to do then is we have to consider matter as something that is not going to change, and so matter is the amount of substance in a body, and that doesn't change unless the body it collides with something or is broken apart. So matter then I'm going to take instead of mass, but then that leaves a gap, because matter alone would have no properties. It would simply be a number, and in fact it's in physics, matter is necessary to tell you the magnitude of an effect, such as, for example, the weight of something. If it has a lot of matter, it's going to weigh more than if it has little matter. If it has a lot of momentum, if it's exerting a force, then all of these things depend on the amount of matter. So matter is really what we call dimensionless variable. It is of the magnitude of something, and energy is not, as mass is the property of a body, but energy is more the property of a relationship between two bodies of matter. We say bodies of mass, which means pretty much the same as bodies of matter, so I will sometimes be using that expression. But energy exists between two bodies. So that we have variables of energy, which is something between two bodies, and we have matter, which is the amount of substance in a body, and then there's time. Now this is not time as we normally use the word. Time here is the difference in time between two bodies, and it's something that Einstein again pointed out as a result of the speed of light being limited, that when bodies travel toward or away from one another, or in fact if they're moving even not necessarily directly toward or away from one another, if they're moving relative to another body, then there becomes a time difference called time dilation. The difference between the time in the two bodies, I'm not going to go into that in any detail, that's not the purpose of this, but time is one of the variables, and this is time as a relationship between two bodies. And then of course there's space, which we're well aware of, and we can see it's the only dimension that is visible, and that is the just as these two, the cleaner and this writer, are separated by space. You can see that, and that's very important. So those are the four fundamental dimensions. Now in addition to that, we need to have something to measure the separation between bodies in space or in time, and difference in energy. And these are called dimensions. Dimensions are the, if you like, the directions, the kind of directions between bodies, so that a body that is separated from another body in that dimension, this might be space, and if they're separated in time, that body is really not there, it's there, and this would be time, and this would be space, which we usually denote by r. So there's the separation in time and in space, and here's the total of those two. These are called dimensions. We need to understand the dimensions that we're going to use in our theory, and we're also going to have natural laws which govern the relationship between bodies, natural laws such as the law for the conservation of energy and the law for the conservation of momentum, and what I call a quantum law, which is a law that says that nothing can exist in infinitely variable amounts. None of these, at any rate, none of the fundamental variables. Those are the things we have to look at in discussing, and then of course we have to go beyond all this. We have to see how these relate to one another in the most fundamental form, and we have to go through the process which has been described as the Big Bang, which occurred right at the beginning, and we've got to talk about what caused that and what happened as a result. So as a result of that, we have to consider how large was the Big Bang? How large can the universe get? And we have some not only some quantum amounts, which are very small amounts, but we also have what I call the very large numbers, VLN, very large numbers. There are some very large numbers which represent maximum amounts. They're important, and we've got to discuss those. And then we've got to discuss how the most elementary particles were formed, and how you got such things as negative and positive electrical charges, and the particles that demonstrate that, such as protons and electrons. Let's talk about something else, and that is a very important part of the theory of everything, will include the question of the different kinds of forces. Force is that which causes acceleration of a body of mass, or an increase in the distance between two bodies, or a decrease in the distance between two bodies in space. And I believe that there's really no such thing as force at a distance where there is no contact with mass. Now that mass, they're including energy fields and energy particles. They're mass. But gravity, for example, which does not, in my opinion, have anything to do with force at a distance. It is simply a question of the momentum of a continued velocity that is viewed as acceleration in space. So such forces as the strong forces that hold together particles at the nuclear level, and even magnetism, electricity, although they are clearly related to energy fields, because you can detect the fields around a magnet or where there's electrostatic force. But in the case of gravity and binding energy, the strong forces, then I think that there's a strong possibility that the strong force is the same thing as gravity, but that's one of the things that will come up in the discussion. Thank you for watching the second video.